Welcome, ladies and gentlemen, to the technical forum at the group exhibit Hydrogen, Fuel Cells and Batteries at the Hannover Fair 2018. I invite you to sit down, order a drink on the house and enjoy the next presentation. Our speaker will be Björn Skúlason, the Sales and Marketing Manager of Hystorsys AS. And his presentation will be on thermal hydrogen compressors that have entered the market. And please welcome with me Mr. Skúlason. All right, there you go.
Thank you. So good afternoon. So we have been developing metal hydride thermal compressors for the last few years, which we are now putting onto the market. So we've done and proven a proof of concept compressors. We've been in operation since about 2012. So we have had different demonstration activities at refueling stations and bottling plants. So we have demonstrated quite a large durability and had thousands of operating hours on our devices. During the last couple of years, we have been focusing on redesign and cost reduction, which is very important before we were able to take the product to the market. The product is mainly thought of for industries or renewable hydrogen and bottling of hydrogen for different applications. And as I said, we are ready to enter the market. There is a certain unique features with the thermal compressor, as it has almost no moving parts whatsoever, which is very different from all other compressors. That means we have very low maintenance costs and extremely high safety elements within the compressor. It's absolutely, or more or less, silent, so you could have it in your room and easy installation. You could wall mount it, and we can actually design it in any way you would like to have it to fit whatever application you would like to have it. When hydrogen goes into the metal hydrides, it actually gets perfectly purified. So if there's any impurities in the hydrogen stream, it actually gets stuck in the metal hydrides. So we can guarantee that the output is extremely pure hydrogen. The key with this thermal compressor, different from others, is that we need heat. So when you have waste heat available, there's almost no energy cost whatsoever. We're only using a handful of valves. So instead, of course, we need waste heat or a heat source of any kind, or access to, for example, geothermal energy. So these were the test units we built. We built a 5 cubic meter an hour compressor where the input pressure was 6 bars and the output pressure was 200 bars. So it was a two-stage compressor system. And then we built a 10 cubic meter compressor where the input pressure was 10 bar and the output was 200 bars. And that's also a two-stage compressor. So these compressors have been running some thousands of hours so far. We have inside our compressor, we have these cylinders full of metal hydride powder. So actually with metal hydrides you can have more hydrogen inside a vessel than if it's empty for hydrogen. So this is just the structure of the metal hydride cylinders we're using. So in a sense, when we have low pressure hydrogen coming into the compressor, we cool down the metal hydride to absorb the hydrogen. And then we actually heat up the cylinders, and then you have high pressure hydrogen going out. So it's a relatively simple operation. So during the redesigning, you can see that this was the original design, and now this is the latest product we actually have delivered. The picture to the left is a slightly smaller compressor, but it has a much lower investment cost. It's very compact now compared to what it was. Much lower temperature requirements. We need a temperature difference of about 70 degrees. So typical, if you have potable water, it's like 10 to 15 degrees. And then you would have to have something like 80 to 95 degrees hot water to actually compress and get the ratio of the compression 4 to 5 times during each stage. And it's very easy to maintain. So typical applications would be standalone hydrogen applications, where, for example, you would have wind or solar energy, and the waste or the extra energy you could produce is actually used for hydrogen production, and then we can compress the hydrogen to bottles for reserve when you don't have access to the renewable source, like at night time if it's solar installations, or when there's no wind or blowing. This is actually one of the applications we have done. This is a standalone system in Sweden, where this house is totally off-grid. So there's a solar installation, and then he uses the extra energy to heat water and produce hydrogen. We compress the hydrogen to bottles, and when he doesn't have access to renewable power, he actually takes hydrogen from the bottles through a fuel cell, and then he has electric power for the house. So this is a totally off-grid house, producing all the energy for the needs. And his goal is also to fuel his hydrogen vehicle. So as you can see, this is a 2 cubic meter compressor. So it's not a very large unit. It weighs only 50 kilos. So it's easy to install and easy to move around. And it's easily scalable in all directions. So you can make the chambers wider, you can make them longer, you can stack them up in any way, any order you would like to have them. The other typical industrial application would be to store hydrogen for example, when you need hydrogen for different industrial processes. They always need backup if you need if the electrolyzer goes down or needs maintenance. Then we can take part of the hydrogen, bottle it for reserves, and then when the industry needs hydrogen, when the electrolyzer is not operating, you have it all from bottles. And this is, in typical industries, you usually have a lot of waste heat, so that is the energy source for the compressor. So as I said, industrial application, bottling on site, utilizing waste heat from industrial processes is the main application. We're also looking at using bottling hydrogen in geothermal locations in Iceland now to increase the pressure, as there will be electrolyzer built at a geothermal power plant. So that's an ideal location to actually use the heat and save a lot of energy. So storing hydrogen from wind and solar installations. Our test units have been at a refueling station in Lillestrøm in Norway, where we actually did the first stage of compression. So we took the hydrogen to 200 bars before it was compressed up to 900 bars for refueling 700 bar vehicles. So this could also be used in combination with high temperature fuel cells. So in a sense, if you have waste heat from the fuel cell or waste heat from the electrolyzer, we can utilize that waste heat to actually compress the hydrogen. And we can bottle hydrogen. And also if you have reformers and a reforming hydrogen, sometimes there's a slight impurities in the hydrogen. And if that actually goes through our compressor, as I said before, we can guarantee that the hydrogen coming out will be absolutely pure. So we have completed all our proof of concepts and operated the compressor for thousands of hours. Throughout the last few years, we've done quite a bit of R&D on the components. The compressor is fully certified with everything, and we are currently delivering metal hydride compressors to different types of customers. And I think we are doing this in a very unique way of compressing hydrogen. And we are in the Norwegian booth, B60, so you're welcome to visit us. We actually have an example of the compressor on display at the booth, so please come and visit us at booth B60. Thank you very much for your attention.
Thank you very much for this presentation, and thanks in the audience for being here. Are there any questions from the audience now? This is your chance. Yes.
Hello, Eva Rav Nielsen, Technical University of Denmark. Thank you for a nice presentation. You say that the compressor uses thermal heat, and if you have industrial processes, there will be heat available. What if there is no heat available, and what if this person's house in Sweden? Can you do the compression just by electricity?
No, you would need thermal energy to do any kind of compression in this unit. So this compressor is specifically designed to use waste heat or where you would have a heat source available. So it's not operational if you don't have heat and you have no moving parts, and you can't increase the pressure of the hydrogen except by having heat. So the lower the heat ratio, or the delta T, the lower the delta T is, the lower the compression ratio is. So, for example, if you would have more than 70 degrees different, the compression ratio increases. If you go down to like 50 degrees temperature ratio, we would have much lower compression ratio than otherwise. But you have to have a delta T to be able to compress with this compressor.
Okay, thank you. Can you tell us the waste heat temperature, how high should it be in optimum?
Well, as I said, we would like to have a 70 degree delta T. So if you have potable water of 10, 15 degrees, which is very typical, we would need 80 plus degrees hot water or steam or whatever kind of heat source. The first actually compressor we built was actually using heated oil inside, so you could actually, we don't care what kind of heat you're giving us, we can actually compress the hydrogen if there's any kind of heat source available. So like, for example, the idea for Iceland is actually to take almost 200 degrees hot water, and at the geothermal plant we also have potable water at 4 degrees, and then we would have 245 degrees difference, and then we think we can have a much higher compression ratio.
Okay, thanks very much. Any other questions?
Thank you for your presentation. Yin is my name, and you tell us after the reformation process. So your compressor process can filter some gas. How it works? You understand what I mean?
Sorry, no.
You know, after reformation, there's some certain gas, maybe carbon monoxide inside. And how can you filter that? Can you tell me us?
We do not filter that. So if you feed us with impure hydrogen with some gases in it, what happens is that any impurities will get stuck in the metal matrix inside the metal hydride. The efficiency of the compressor goes down the more impurities you're going to feed into the compressor. So the only thing I can guarantee you is that you get pure hydrogen out. The purer the hydrogen that comes in, the longer lifetime you have of the metal hydride. But if you feed me with a lot of impurities like CO or CO2, it all gets stuck in the metal hydride. But over hours or over some thousands of hours, the efficiency of the compressor will go down because all these materials are being collected inside the metal hydride.
And is it then possible to refresh the material somehow?
Yes, it's easy to actually disassemble and take out the metal hydride is inside in a pipe inside, so you can actually easily take the pipe out, replace it with a new one, and we recycle the metal hydride again for the next use.
Okay, thank you very much. Are there still questions? Yes?
For the example of the house, what kind of energy of heat the compressor can be used for reuse the waste of heat?
So
What, for example, in the house, you show us a house. What kind of heat do you need for reuse and feed the compressor?
actually at the house, there is excess solar energy during daytime, and he is a boiler, so he uses that to heat the water up to 90 degrees. So we then use the water for our compressor, and it loses about 10 degrees in our compressor, and then actually it enters the house for heating the house or the showers or whatever. So we can actually recycle the water in that way.
So do I understand it right that your aim is to use renewable energies to supply the heat?
That would be the ideal situation, to have either solar, wind, geothermal, anything which is renewable.
Okay, thanks a lot. As he already mentioned, you can find him at the booth number B60. Thank you very much.
Thank you.
Okay, and the next presentation in 5 minutes will be on advanced production methods for high efficiency electrodes for the production of hydrogen from the Fraunhofer IFAM. See you there.